There's no difference between a planet and a star. Not philosophically. Physically. Jupiter is made of hydrogen. The Sun is made of hydrogen. The only thing separating them is how much hydrogen they managed to collect before gravity stopped being patient. That border, the point where gravity turns matter into fire, isn't drawn by category. It's drawn by mass. And just below that line, in the space between planet and star, there are objects that tried to ignite and failed. They're still out there, glowing faintly, waiting for nothing. When we talk about stars, we're talking about fusion. Hydrogen nuclei crushed together under so much pressure that they merge, release energy, and light up the galaxy. When we talk about planets, we're talking about objects that never got hot enough for that to happen. They formed, they cooled, they stayed dark. But the dividing line between those two states isn't clean. The Sun weighs about 1,000 times more than Jupiter. That's the gap. But it's not a gap in composition, both are mostly hydrogen and helium. It's not a gap in structure, both have cores under pressure. Both generate heat from gravitational compression. The gap is just mass. And somewhere between Jupiter's mass and the Sun's mass, there's a threshold. Cross it, and fusion starts. Stay below it, and you stay cold. That threshold isn't arbitrary. It's set by the physics of atomic matter under extreme pressure. And the objects that land just below it, too heavy to be planets, too light to be stars, are called brown dwarfs. They're the closest thing the universe has to a failed star. The problem isn't figuring out what a star is. The problem is understanding why gravity doesn't always win. Because gravity should win. If you pile enough mass into one place, gravity pulls inward. The core compresses. Temperature rises. Eventually, if you compress hydrogen nuclei close enough and fast enough, they fuse. That's the expectation. But it doesn't always happen. There's a force that resists gravitational collapse. And it's not pressure from heat. It's not gas pushing back because it's hot. It's a quantum mechanical force called electron degeneracy pressure. Electrons don't like being in the same quantum state. When matter gets compressed to extreme densities, electrons start running out of available states. They push back, not because they're hot, but because the rules of quantum mechanics don't allow them to occupy the same space. This pressure doesn't care how much you heat the gas. It only cares about density. And for objects below a certain mass, electron degeneracy pressure is strong enough to stop gravitational collapse before the core gets hot enough to ignite fusion. If that sounds like matter has its own opinion about becoming a star, hit the like button, because this resistance is real, measurable, and it's why brown dwarfs exist. Start with a cloud of gas. Hydrogen, helium, trace metals. Gravity begins pulling it inward. The core compresses. Density increases. Temperature rises, not from fusion, just from gravitational energy converting into heat. The object starts glowing faintly in infrared. It's radiating heat, but it's not burning anything. Inside, electrons are being forced closer together. At first, there's space. Quantum states are available. Compression continues. But as density climbs, electron degeneracy pressure starts to matter. It's not dramatic. It doesn't reverse the collapse. It just slows it. The core compresses, but more slowly. Temperature rises, but not fast enough. The object keeps gathering mass. If it collects enough, around 80 times Jupiter's mass, the core pressure eventually overwhelms electron degeneracy. Temperature climbs past 10 million Kelvin. hydrogen nuclei collide with enough energy to overcome electrostatic repulsion. Fusion ignites. A star is born. But if the object doesn't gather enough mass, it stops short. The core compresses until electron degeneracy pressure balances gravity. Temperature plateaus. Fusion never starts. What you're left with is a brown dwarf. From the outside, it doesn't look like Jupiter. It's massive enough that its own gravity crushes it into a near-perfect sphere. Banded cloud layers wrap around it, ammonia, methane, water vapor, but the clouds glow. Not from reflected light. From internal heat. The surface temperature can reach 1000 Kelvin. Hot enough to emit a dull, deep red glow. Some brown dwarfs pulse faintly in infrared as their atmospheres churn. The texture isn't solid. It's thick. Banded gas sliding over itself in violent convective loops, radiating leftover heat from gravitational compression that happened millions of years ago. It looks like a bruised star. Magenta and purple bands streaked across a sphere that's too hot to be a planet and too dim to be a sun. And it's cooling. Slowly. Over billions of years, the internal heat leaks into space. The glow fades. Eventually, it goes dark. There's no ignition coming. There's no second chance. It missed the threshold, and physics doesn't negotiate. If you want to see what happens when gravity loses, subscribe, because the rest of this channel is built on understanding why most attempts fail. The transition from brown dwarf to star isn't gradual. It's a threshold. Below roughly 80 Jupiter masses, the core never reaches the temperature needed for sustained hydrogen fusion. Deuterium, a heavier isotope of hydrogen, can fuse at lower temperatures. And some brown dwarfs do ignite deuterium briefly. But deuterium is rare. It burns out in a few million years, and the object goes quiet again. Hydrogen fusion requires more. It requires core temperatures above 10 million Kelvin. And densities high enough that protons collide billions of times per second. And that only happens when gravitational pressure overwhelms electron degeneracy completely. At around 80 Jupiter masses, that finally happens. The core compresses past the point where quantum resistance matters. Temperature spikes. Proton-proton fusion begins. Energy floods outward. Radiation pressure pushes back against gravity, and the collapse stops. The object stabilizes. It's no longer just radiating leftover heat. It's generating new energy. It's a star. The difference between 75 Jupiter masses and 85 Jupiter masses is the difference between a dim, cooling object and a furnace that will burn for trillions of years. Not because one is special. Just because one crossed the threshold and the other didn't. The 80 Jupiter mass threshold is approximate. The exact value depends on chemical composition. Stars with more metals, elements heavier than helium, reach fusion at slightly lower masses. Because metals increase opacity, trapping heat in the core. Stars with fewer metals need more mass. We also don't know exactly how many brown dwarfs exist. They're faint. They don't emit much visible light. Most detections come from infrared surveys, and those surveys are incomplete. The boundary between the heaviest brown dwarf and the lightest star is also fuzzy in practice. There are objects near the threshold that show weak fusion signatures, but not enough to stabilize long-term. They're transitional. We can measure their mass, but classifying them requires assumptions about internal structure we can't directly observe. Models indicate that electron degeneracy pressure behaves predictably at these densities. But we can't put a probe inside a brown dwarf's core to check. We infer pressure from mass and luminosity. The physics is solid, but the application has margins. If you think uncertainty makes the threshold less real, share this video, because the line exists whether or not we can measure it perfectly. The threshold is set. 80 Jupiter masses, give or take. Cross it, and hydrogen ignites. Stay below it, and you cool in the dark. But that clarity creates a bigger problem. If stars require that much mass to ignite, where does that mass come from? You can't build an 80 Jupiter mass object out of scattered gas. You need concentration. You need a region of space where hydrogen is already dense enough, cold enough, and stable enough to collapse inward without dispersing. You need an environment that can gather and hold that much matter in one place long enough for gravity to finish compressing it. And those environments don't exist everywhere. They're rare. They're cold. And they operate under conditions that shouldn't allow anything to form at all. Does the mass threshold feel less important now that you don't know where to find enough gas to cross it? Let me know in the comments.